Hello, good afternoon, welcome, thanks for coming. My name is Stuart Marks. I work in the core libraries team on the JDK at Oracle. My Twitter handle is Stuart Marks, you can see here, and I answer a lot of questions on Stack Overflow, so you can see my badge and all those fake internet points I have. So this talk is Collections Corner cases. If you have any questions that I don't get to in the talk, please tweet on this hashtag, and I will be monitoring this after the talk, and if you have any follow-up questions, I'll be happy to try to answer them. Okay, so the talk is Collections Corner cases. I'm going to be covering two different subjects in the collections. And this is kind of an interesting talk. There's so much cutting-edge new material going on here at Devoxx. Everybody always likes to learn about new things that are being developed and introduced. And so it's really cool to see a really crowded room to hear some stuff about the collections framework, which was introduced all the way back in JDK 1.2. And in particular, most of the stuff I'm going to be talking about has been in the JDK since that time. And it's just some things that have always been there but are very easy to overlook, and they're a little bit obscure, but they're also very useful and very powerful. So that's what we're going to be covering today. This talk is divided into two parts. One is what I will call view collections, and the second part is sorted collections. And you may have heard that with sorted collections, there is this notion of a comparator or comparison method and a concept of consistent with equals, which is an extremely confusing concept that is backed up by an exceptionally poor specification text. So I will be covering that in detail later on in the second part of this talk. Okay, view collections. So I think most people are familiar with conventional collections like ArrayList and HashMap and so forth. These collections contain their own elements. Now, fundamentally, the only aggregate structure in Java is an array. So these actually store things inside arrays inside of themselves. But nobody outside of an ArrayList or HashMap has access to those internal arrays. Now, on the other hand, a view collection does not store its own elements. Instead, it's sort of a facade that provides a view of elements that are stored somewhere else. And so what's interesting about this is that if you can modify the view, that sort of writes through to the underlying thing. And if you write to the underlying thing, then that is visible in the view. So here's a little example of some code here that does that. So I've initialized the string array with some strings, and I've created a list using arrays.asList, and I pass that array into it. So now the list that is returned by arrays.asList is a view onto that string array. So now if I modify the first element of that string array, it has the effect of apparently also modifying the list at the same time. And also, if I call set on that list and set an element to something else, then of course that modifies the list, but it also writes through to the underlying array, and the array's contents have changed. And this is also a little bit of a surprise to some people. Sometimes there's a misconception that the list returned by arrays.asList is immutable, and that is not true. You can definitely change it by calling set on it. What you can't do is add or remove elements, and the reason for that is you cannot change the size of an existing array in Java, but you can set elements in it. So such a list is not immutable. All right, so here's a diagram that showed what went on in the previous slide. We have the list returned by arrays.asList, and it doesn't contain its own elements. It looks like it contains elements, but really those elements come from the underlying array. And so if you get something out of that list from arrays.asList, it actually goes and pulls it out of the underlying array. If you set something into the if you set something into that list that was returned by arrays.asList, then it pushes it through all the way down into the underlying string array. Okay, so that's kind of a very simple view, and so what I want to spend most of the time in this section of the talk on is some view collections on the map. And so these are much more powerful and interesting and very flexible. So again, let's start off with a hash map, a map from integer to string, and you initialize that with a hash map, and let's just assume we've added some things to it, populate it with some contents. And now, so the next few lines in this slide create view collections that are based on or that are backed by this hash map. So the first thing is a key set. We can call map.keyset, and that returns a set view of the keys of the map. Now, so the keys of a map are unique, and so it makes sense because for the view of the keys to be a set, because of course a set must contain unique elements. The next view is the values collection. So you can say map.values, and you get a collection of string, which is the type of the values in that map. Now that's a collection. Why is it a collection? Well, values in a map don't have to be unique at all. So it's not a set. And also the values in the map don't have any order defined. So in general, maps do not have order defined, although we're going to be talking about a different kind of map later on. But in general, the entries in a map don't have any ordering on them. And so the values are not in a list either, because a list has an implication of order. And so really, what we get is a collection. And so collection is just a bunch of elements, no order defined, might or might not have duplicates. So that's the values view as a collection. And then finally, we can get the entry set of a map. And that is a set of this thing called map.entry, which is one key value pair. And so that's a bit of a mouthful, but I'll have some diagrams that explain that in a little bit. Excuse me. So the map.entry is an interface with actually a whole bunch of stuff in it, but the main things are an entry is a key value pair. You can get the key out of a map entry, you can get the value out of a map entry, and also, interestingly enough, you can set the value, but you can't set the key. So that's very interesting. I'll have a demonstration of that later on. All right, so let's talk about what these views really are. So at the bottom of the screen, I have a diagram here that shows a hash map that is a map from integer to string. And so the point of a map is you can say, I have some integer and I want to look up the string that corresponds to it. So the top row is the keys, and so if you have some integer value, you can look up. Sorry, if you have an integer, you can look up that in the map and get the corresponding string out of it. So every key has a corresponding value. All right, so that's what a map basically is. Now, what happens if we get the key set view of a map? So if you call key set, then you get a set back, and the type contained in the type of that set is the same as the keys of the underlying map. But remember earlier I said like arrays.asList, it doesn't really have the elements itself. It's merely a view onto some underlying collection. So the key set view is a set of keys, but it doesn't contain them itself. Instead, it's actually a representation of the keys that are actually in the underlying map. Similarly, with the values view, I call map.values, and I get a collection of strings back. And there I get a collection that represents the values that are actually inhabiting the underlying map. And finally, we get the entry set view. And so this is a little interesting. So we get back a set of entries, and remember, each entry is a key value pair. So it's like, this is a little weird. So how is a set of entries different from a map of integer to string? Well, it's exactly the same information, it's just in a different shape. And so you can operate on it like a set, whereas you cannot operate on a hash map like a set. So it's representing exactly the same information, and in fact, once again, the entry set view does not contain the elements itself. It's a differently shaped view onto the underlying map. All right, so let's put this knowledge into action here. What I have is a J shell. Let me make that a little bigger. All right, I've preloaded some information into my J shell here. So I have a variable called map which is contains a mapping from integer to strings. /var in JShell does not have anything to do with the var keyword introduced in Java 10. It's an unfortunate overlap. /var asks JShell to describe this variable. So what is map? Map is a hash map from integer to string, and it contains the following key value pairs. Okay, so that's pretty straightforward. All right, so let's create our map views here. So we get the key set. All right, so the key set is a set that contains just the keys. Okay, that makes sense. Values is get the values out of the set, and that is a collection that contains just the values from the map. And let's get the entry set. Okay, and so it's interesting because the entry set it looks like it's the same thing. So if we look at the type of entry set, it is a set of map.entry of integer.string, quite a mouthful. Whereas if we look at the definition of map, then it's a hash map from integer to string. So again, it's the same information, it's just shaped differently. Now, what can you do with this? So let's put a new value into the map. So I'm going to put mapping from 6 to f in the map. And so the return value is null, which is the previous value that was mapped to 6. And since there was nothing previously, that's why the return value is null. But if we look at the map, we again see, oh, okay, well, pretty clearly we've added a mapping to the map. Okay, that's nice. So let's look what happened to the key set. There's another key there, which is 6. Similarly, if we look at the values, there's another value, which is f, that appears at the end. And shouldn't be surprised that entry also appears in the entry set. So notice I didn't have to get the key set or the values. I didn't have to call those methods again to create those views. The view is it's a live view of what is actually in the map. And so if the underlying map changes, then the live view changes kind of automatically with, you don't have to do anything to refresh it or anything like that. Now, what's interesting is these are collections, and they are mutable collections, and you can modify the views. So let's take the key set and remove one of the keys from it. So true means the collection was actually modified. And so you can see 3 is gone now. That makes perfect sense. But if we look at the underlying map, the mapping was actually removed from the underlying map as well. So the key set is not merely a set of keys, but it's also just a projection of the keys that happen to be in the underlying map. And if you perform side effects on the key set, such as removal, those actually affect the underlying map. So one thing you can't do is add entries to any of these views. That's simply not supported by the collections framework. And you get unsupported operation exception if you try to do that. But removal is sometimes quite useful. So we can remove elements one at a time. Oh, actually, I also want to say, if you look at the values, of course, the values view shows that the corresponding value has been removed, corresponding to the key 3 that we just removed. Okay, so we can do side effects on these maps. We can also do bulk operation side effects on these map views. So if we have the key set that has these keys representing the keys of that map, so let's do a bulk operation remove if on the key set. And so this is a set of integers, so I can say let's remove the even ones. So let's remove if k mod 2 is 0. Okay, returns true, meaning that the key set was actually modified. And what do you know? All the even keys have been removed. And if we look at the underlying map, all the entries corresponding to those keys have also been removed. So that's kind of nice. You can operate on the map by operating on one of the map views, like the key set in this case. And that also applies to values and the entry set. Now, the entry set is a little weird because kind of in the old model, it was the best way to do bulk operations on a map in the absence of streams. You would write some for loops using an iterator over the entry set, which is a little strange. Nowadays, we can use streams, or we can use the map.forEach to get a succession of keys and values. So I'm not going to show that, but I will show one thing, which is that you can use the entry set to make side effects upon the underlying map. So we can say, okay, so let's look at that entry set. Now let's get the iterator of this entry set. And all right, so blah, 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 HashMap $entry iterator. So let's see what the type of that is. It is an iterator of map.entry from integer to string. And now let's get the first element out of it. So we'll say var entry equals it.next. So I'm not going to, okay, I know there are entries in here. I'm not going to bother calling hasNext, but you really need to do the hasNext, the old-fashioned iterator style loop. And so the entry I've retrieved from that iterator is the first one, which is the mapping from 1 to A. Okay, so now that I have an entry, I can say get key gives me 1, entry.getValue gives me A. But I can remember, back I showed the interface, there's also a set value. So I can say entry.setValue. And okay, now it's a little weird. It returns the previous value. So the return value is the previous value that was replaced by the XXX. So if I ask for what the entry is, clearly now it's a mapping from 1 to XXX. But wait, this is a view of an underlying map. So if we go back to the map, it had a side effect of changing the map as well. So sometimes this is useful. You can iterate over the entries and do some interesting modifications to the map in place. All right, let's return from the demo. All right, so there's some times when map views can be quite effective at doing operations on collections, quite a bit, even sometimes more effective than streams operations. So for this example, I'm pulling a page from my old playbook, which is most of the material for my conference talks comes from Stack Overflow, and so. So this is actually an interesting question. This person had a problem, which I've restated in a very concise fashion here. So the questioner has 2 maps, and the maps are of the same type. And I'm just using integers and strings here. I think that's what the person originally had. But the task is to find the values that the maps have in common, and then, sorry. Well, yeah. If you have the value, if you find the values that are in common, then get the keys from map B that are corresponding to the values that they have in common. And so that's a little bit backwards because you're working backwards from values to keys. And maybe there's a way this person could have rearranged the data structures, and maybe there isn't. But this was the problem the person had. And so if you look at this simple example, we have maps from strings to integers, and you can see that the common values are A and C, and so therefore the keys in map B that correspond to those common values are 5 and 7. And then there's another wrinkle here, which is actually significant, which is the questioner said, oh, I also have a lot of entries here. For some reason, he had 15,000. And so the complexity of the algorithm is actually significant. So we have to pay attention to that. All right, so the questioner was pretty good. He came up with an initial attempt at it, and he said, well, I wrote this code, and there has to be a better way. So, please, Stack Overflow, can you tell me if there's a better way? And so if you look at this, I'm not going to go through this in detail, but basically it's streaming over the key set of map B, and then filtering by streaming over the key set of map A, and then seeing if the values are equal, and then if the count of the values are equal, then that means they must be in common. And so once you've done all that filtering, then you get the entries that it has in common, and you get the keys for the entries that it has in common, and then you collect that into a set. So that's pretty complicated. And if you don't understand this, it's not really that important. You can piece through it later at home. But really, the thing here is this is like a nest. having a stream operation inside of a stream operation is like a nested loop. And so if you have 50,000 entries in each map, then you're going to run you're going to be running an n-squared algorithm over a large number of entries, and that is going to take a long time. And I actually ran this. This took several seconds to do the job. And so collections operations like this really should not take that long. And so I think the questioner was right to say, hey, I wrote this code. There has to be a way to improve it, and I have a lot of entries, and I want to make sure to reduce the complexity. There's an answer that came in, and this is what really gets me going on Stack Overflow. When somebody posts an answer and says, oh, here's how to do it, and then the questioner actually accepts it, but it didn't solve the problem. So the alternative answer was to simplify the streams, the nested stream pipeline somewhat. And so this is a little bit nicer, but it's basically doing the same thing. We're streaming over the entries of map B, and then we're filtering those entries if A's value collection contains this entry's value. Okay, so that kind of makes sense. And then now that we have entries that correspond to matching values, then we get the key and collect those into a set. Okay, now there's a wrinkle here, which is this is still n-squared, because, so you see in the middle of this, there's map_a.values. That is a values collection. That has no organization. And so if you call contains on it, it has to do a linear search through it. So hidden in this, we're still doing a linear search inside of a stream over all the entries, and so we're back to n. Well, we never left n-squared. We are still at n-squared. So it's a little nicer code, but we still have the same problem. So let's think about this a little bit. The key here is we want to do a contains operation on values. And so if we do map_b.values.contains, then we do a linear search. Well, we're searching the same thing every time, so if we're willing to pay a little more space, let's collect those values into a hash set, and that reduces the contains operation from linear to constant. And so since we're doing that for every entry, then we've reduced n-squared to linear. Okay, so that's what we were going to do, and so the next code here is a slight optimization of that, which is we bring this into, we first bring A's values into a hash set, and then we have the same algorithm here where we stream over map B's entries, see if A's values contains this value, filter it, get the key, and collect that into a set. And that's much better. Certainly algorithmically, that's much better. That does reduce it to linear. The code is kind of complicated because streaming over the entry set is a little bit cumbersome. I think you can improve on this still. So quick aside about set operations in the collections framework. Quite often you want to do something, set operations like union or intersection and things like that. But there are no methods with those names. And it turns out that retain all is the way to do set intersection. And if you look at these Venn diagrams, it turns out that that's exactly what you want. And you have to do it the right way. You have to say A, actually, did I get that right? Yes. If you start off with A and you say retain all of the elements that are in B, then in fact you get the set intersection. See, that's why it's confusing, right? So from one standpoint, if you describe it that way, then it makes perfect sense. On the other hand, if you want to do set intersection, you have to puzzle over it a little bit. So anyway, so retain all is the thing that we want. We want set intersection because remember the problem statement is for the values that map A and map B have in common, right? And that means the set intersection. Okay. So how can we improve on this? Well, we have view collections and we have bulk operations on those view collections. And so I think we can improve, and side effects on those view collections have affect the underlying map. So we can use all that information to improve on the previous code. And then also we don't have to copy we don't have to copy the keys into a new set. We can just use a key set view. All right, so let's look at the code that does that. All right, so we have our two maps. The first thing we do is the same as before, which is we bring map A's values into hash set because we're going to be doing a repeated contains check on that. Now, this is one of the things about collections is that since there are side effects, if you don't want to modify your inputs, you have to make copies first. So we make a copy of map B, and then we get the values collection from the map B copy, retain all of the values from A. And that, in fact, if you look at it very carefully, that calls contains repeatedly on A's values, so it's still important to have that in a hash set. But that's computing the intersection of A's values and B's values, which is exactly what we wanted. And so that leaves the right set of entries in the copy of map B. And since the problem statement was we want the keys that correspond to the common values, we just get map B, the copy of map B's key set, and that's our result. So I think this is a little bit better than the streams code. It's 4 imperative statements. It does do some more data copying, perhaps. The streams code has some lambdas in it and stuff. I'm a big fan, as you know, of streams and lambdas. I think it's a great API, incredibly useful for things. But sometimes you just don't need to use it. Sometimes you can fall back on these collections bulk operations, and they can be very powerful. All right, so this is the end of the first part here. So I think I basically said that. Yeah, view collections are powerful. You can do bulk operations. It's easy to forget them, and so I think it's just another set of tools in the toolbox. You can write more effective code using this stuff. All right, let's move on to part 2. All right. So there's a whole family of interfaces that are sorted. There's sorted set, sorted map, navigable set, and navigable map. That's kind of a mouthful to say. And there are a few implementations: tree set, tree map, concurrent skip list, set, and map. They all have kind of the same properties. So henceforth, I'm just going to say sorted set because it's the easiest one to work with. But this really applies to all of these. Key point here is that the sorted collections are ordered by a comparator or a comparison method of some sort. And the issue that I'm going to spend some time describing is that there is a possibility that the comparator might or might not be consistent with equals. And so I will take some time to explain what that means. But first of all, let's do the basics of the sorted set here. So if you have something like a hash set, one of the things about the hash set, and also the new unmodifiable sets like set.of, is the iteration order is undefined. So if I load these string values in, I might get them, I will get them all out, but the order in which I get them out, if I iterate them, is not defined. Now for sorted set and all those other interfaces and implementations, the order is well defined. Now, what is that ordering? Well, it is the order that is imposed by the comparator that you provide when you create that set. Now, there are a variety of other ways to provide the comparison method. I'm just going to stick to a comparator because it's a crisp way of, it's an interface with a single method on it, and we can define those easily using lambdas. And so I think that makes the illustrations clearest. But there's also these, some types have a natural order, and the same issues apply to them. But anyway, so I'll be focusing on a comparator on sorted set. All right, so what is a comparator? So it's an interface. It has one abstract method, which takes 2 objects of type T, and it returns an int that says what the relative ordering of these 2 objects are. All right, and so the integer is less than 0 if A is less than B, it's 0 if A is equal to B, and it's greater than 0 if A is greater than B. There are a bunch of rules here which have some mathematical basis. Suffice to say that they're actually pretty intuitive, so I'm not going to spend too much time on them here. The point is that the comparator must impose a total ordering on all of its input elements. So that means basically for any two elements, you have to provide a result. You can't throw an exception or anything. But also the results must be consistent. So if you compare A and B and you get some result, and then you switch them, then the sign of that result should be the opposite of what it was, right? So if A is less than B, then pretty clearly B must be greater than A. It's actually pretty easy to write a comparator that has bugs in it, but let's set that aside for the moment. That's the subject of a different talk I gave here a couple years ago. But anyway, so there are a bunch of comparisons that are total ordering, which are pretty intuitive, like a case-sensitive alphabetical order of a string, right? You can sort any string. Any string compares to any other string, and it's all consistent, and it makes sense. I think intuitively most people get that. All right, so let's look at some comparators here. Back to JShell. All right, so I'm going to declare a comparator of string, and I'm going to call it CSO for case-sensitive ordering. And what I'm going to use is the strings compare to method. All right, so that's some Lambda expression, whatever. The point of CSO is that is a function, and so I'm going to call the compare method on it and show you some things there. So okay, CSO.compare A and Z. A is less than Z, so the result is negative. Okay, CSO.compare Z and A. And it's greater than 0, so Z is greater than A. And so we compare Z and Z. It's 0. That means they are equal. Okay, pretty simple. All right, now I have a set of strings. Whoops. I have a set, sorry, this is a list of strings, and I've pre-populated it with some various strings here. And what I'm going to do is I'm going to load these strings into a tree set that uses this case-sensitive ordering. Okay, so the tree set constructor takes a comparator, and so it creates an empty set that has that comparator in it. So now I'm going to load those strings into it, and so it says true because it modified that. And now, what do you know? They're sorted. Pretty good. Okay. And if I add some more things, like CZ, for instance, then, okay, that new thing got sorted into the right place in alphabetical order. And if I add something else, then, okay, that went at the beginning. All right, that makes sense, right? So we all know about character encodings, and so capital letters come before lowercase letters. So TTT, capitals, comes first before all those lowercase ones. All right. So what's the difference between tree set is like a sorted collection. Isn't that like a sorted list, right? So I could say, so I could create a list here. And so I could sort that list using the case-sensitive ordering. And I get the same thing, right? So what's the difference? Why should I use a tree set instead of a sorted list? All right, so if I do list.add, and let's add some more elements here, and then sort it. Okay, so I added BB, which was already in that list, and then I sorted it, and so two BB elements ended up next to each other. So a list allows duplicates, and so if you sort them, then the duplicates will end up next to each other. Now, if I clear that tree set, remember, a tree set is a set, which means it can't have duplicates. And so I loaded all the elements from the list into the tree set, and it compressed out the duplicates. So that's the difference between a tree set and a sorted list. All right, back to the slides. Okay, so a key point is that the comparator not only determines ordering, but this is totally unclear from the documentation, but it is true. The comparator of a tree set also determines membership in the tree set, and this is very easy to forget and is a source of a lot of problems. So the rule for something like a hash set, which everybody uses, is that it can. I kind of glossed over this a moment ago. I said a set can't contain any duplicates. Well, what's the definition of a duplicate? If you have a hash set, the definition is A and B are duplicates if A dot equals B is true. So a sorted set has a different rule for determining when they're duplicates. In particular, it calls the compare method of the comparator. And so A and B are duplicates if the compare method, when called with A and B, returns 0. It does not use equals. Okay, so here you can see we're setting things up here. There's a different notion of some kind of equality. Actually, revisit here. So again, earlier I kind of glossed over this. I said the comparator returns 0 if they're equal. Well, it's not equal in the sense of object.equals, sort of equivalent in whatever ordering that this comparator is imposing. And so it's the comparator supplying the semantics here. What does it mean for this comparator to return 0? Well, it depends what the comparator does. It depends what the intent of that comparator is. But the key is that the comparator returning 0 is what determines membership is in one of these sorted sets, not object.equals. And that is the source of a lot of confusion. Now we're coming to consistent with equals. So you say, well, if I have two objects and I call equals on them, then of course, if I call compare on them, then that should return 0, right? I mean, that's kind of obvious, right? And a lot of the times it's true. And so the spec has some words to say about this. It's like, well, actually, it's possible that the comparison method is not consistent with equals. And then it says, caution should be exercised, blah, blah, blah. If the ordering imposed by the comparator on a set is inconsistent with equals, the sorted set may behave strangely. Okay, thank you. In particular, the sorted set will violate the general contract for set, which is defined in terms of equals. Okay, well, nobody knows what this means. And I have to say, this is a remarkably obtuse piece of the specification, and I have some ideas for how to fix this. But really what this means is that it's the difference between comparison returning 0 and equals. Those are different, and so if they're not consistent, then we can see some strange effects, as we'll see in a moment. Now, let's look at the sorted set specification and see if it can shed any light on this. Okay, so there's another big wall of text here. I'm not going to bother to read all this, and neither should you. The kicker here is the behavior of a sorted set is well defined, even if its ordering is inconsistent with equals. It just fails to obey the general contract of the set interface. What does that mean? I think that is incomprehensible. So what I'm going to do is show you what that does. All right. So previously I had CSO, which was the case-sensitive ordering. So we say CSO.compare, and I'm just going to give it two strings here, A and A. All right? They compare to 0, and I mean this is sort of obvious, but you got to type it out to see it. A.equals A is true. Okay, so I claim that the case-sensitive order comparison is consistent with equals. Okay, and so you could try it for every value and so forth and prove it, but basically, if the comparison method returns 0, equals returns true, and vice versa for any pairs of values. Okay, but what comparator could possibly be inconsistent with equals? And it's sort of hard to get your head around, right? If we're sorting strings, it's like, well, strings, you sort them, and it's like, how can the comparison not be 0 if they're equals? Or how can equals not be true if the comparison is 0, more to the point? It turns out that Comparators that are inconsistent with equals are much more common than you might think, and in fact, they are built into the JDK. There's one right in the string class, and so I'm going to start using it here. I'm going to create a comparative string called CIO, case insensitive ordering, and there's one on the string class defined already. Okay, so let's call the CIO comparator on some values. Okay, if I compare lowercase a and lowercase a, I get 0. If I compare lowercase a and uppercase a, I get 0. Well, of course, because we're doing a case-insensitive comparison. So lowercase and uppercase are equal, right? But of course, a dot equals capital A is false. So right here, we have a comparison method, or comparator, that is inconsistent with equals. Since it returns 0, but the two values that pass to it are decidedly not equals. Now, sometimes you'll run into people who say, oh, well, this is a bug. You should never use comparison methods that are inconsistent with equals and so forth. And in fact, it does have strange effects. That's definitely true, but it is not a bug. They're incredibly useful, right? People like case-insensitive sorting. And so the fact is that that's inconsistent with equals. So what are you going to do? You have to understand what goes on here. All right, now let's try using a tree set that uses this case-insensitive ordering. So I'm going to create another tree set, and this time using the case-insensitive ordering. And so I'm going to add some things to it. What did I have here? M, capital A, and lowercase a and lowercase c. Okay. So I added a few things there, and if we look at the list of the results here, oh, okay, well, that kind of makes sense because we're doing a case-insensitive ordering. Then even though those capital M's, the capital letters, the character encoding values are less than the lowercase encoding values, since we're doing case-insensitive ordering, they come in the middle. Okay, that makes perfect sense. So now let's call contains on this. So clearly, the tree set contains capital M's. Oh, but it also contains lowercase m's. That's a little odd. But of course, we told the tree set, do case-insensitive comparisons. So yes, lowercase m's are equal or equivalent to uppercase m's. Yeah, okay, yeah, you get your head around this, but it does you start to see that this notion of contains is a little odd here. Now, what happens if you mix hash sets into this? So let's create a hash set. And I'm going to populate it with the elements from that tree set. And so clearly, the hash set contains capital M's. But of course, it does not contain lowercase m's because lowercase m does not, if you call object.equals, it returns false. So the hash set does not contain lowercase m, but it does contain uppercase m's. Okay, that makes sense. I think that's the behavior we're used to. There's nothing to tell a hash set to use case-insensitive ordering or anything like that. There's no ordering at all. It's just equality. Okay. Now we have two sets here. We have a tree set and we have a hash set. And what happens if we compare sets for equality? So there's a well-defined notion of equality of sets in the collections framework. It's basically, if I say hash.equals tree, two sets are equal if they have the same number of elements and if every element of that set is also in this set. And so how do you say if something is in this set is you call contains? So let's think about this a little bit. Does the hash set equal the tree set? I think so, because if you look at all the elements of the tree set, everyone is in the hash set. Okay. Now is So let's go the other way. Okay, well, actually, that's kind of obvious. Now I'm going to modify the hash set a little bit. And I'm going to remove the uppercase m's and add lowercase m's. So now if I say hash dot equals tree, so remember, for every element of that other set, is it contained in this set? So if we look at the tree set, it contains capital M's, but the hash set does not contain capital M's. It contains lowercase m's. So I claim this is going to be false. Okay, that makes sense. What happens if we do it the other way? Tree equals hash. Okay, so we go through every element of the hash set and say, is that element contained in this tree set? True. Okay, so that's kind of weird, right? So this is what that wall of text in the spec was saying. It behaves strangely because you can have two sets, one of which claims it is equal to the other, but that other set claims that it is not equal to this one. So that's kind of weird. So the lesson here is if you're using a sorted set with a comparison method that is not consistent with equal, you have to be very, very careful. In particular, don't mix them with other kinds of sets like a hash set, because you will get into trouble. All right, well, so is this just a corner case that I don't have to worry about in day-to-day programming? I don't think so. Okay, so let's see, I went over this already. So this is what it means by violates the general contract of set and behaves strangely. It's this difference between this inconsistency with equals. All right. All right, okay, so I'm going to go straight on to the next demo. So does this come up in real life? Yes, and in fact, I'm not going to cite them here, but there have been other Stack Overflow questions where, oh, I'm getting this weird behavior, why is this happening? And so this is an example I cooked up based on some of those. I have created an employee class here, and there's a bunch of code here, but it's pretty obvious what it does. It's an employee with a name and a salary and an obvious constructor and a toString and equals method and stuff. So there's nothing really sophisticated here. It's an obvious value class. Okay, so there's I have a list of these employees, and let's print them out in a nicer format here. Println. Okay, so we have a list of 6 employees here, very good, and their salaries. Okay. Now, I want to sort them. Let's sort them by salary order. So let's come up with a comparator of employee. Comparator.comparing employee get salary. There we go. Okay, so that's a comparator, and just to show it in action, here, let's look at that again. All right, so let's sort the employees. Now this is a list, so we're just going to call sort on it, and we're going to use salary order. And then let's look at that again. Great, our employees are sorted by salary. Now, your manager comes to you and says, you know, we're going to be doing a bunch of layoffs. Excuse me, we're going to be doing a bunch of reorgs and shuffling around. So instead of having to modify the list and sort it every time, I want you to keep the employees in a data structure that is kept in sorted order. And you'll say, great, this guy Stuart Marks was at Devox last week, and he told me how to use a tree set. So let's use one of those. That's really cool. So let's add the employees to a tree set and sort them by, oh, and of course your manager wants them sorted in salary order, so we have a comparator that does that already. And so we add all of the employees to that tree set. Oh. And I'm going to print them out in a nicer form here. And what happened? Oh, Pat is going to be really upset when they don't get their paycheck at the end of the month, right? So what happened here? We told TreeSet to sort by salary order, but remember, the comparator also determines membership. And since Pat and Terry have the same salary, the comparator considers them duplicates. And they're not duplicates because, of course, Pat and Terry are not equal. So this comparison is inconsistent with equals, and if you use it without thinking about it too much, you will get serious problems like this. And in fact, this does come up in the real world. So what should you do about this instead? There are a couple ways. You can write a more sophisticated comparator that makes sure that every employee is unique, like also sorts on the employee ID, or don't load them into a tree set. Keep them in a list and sort them, because sorting a list does preserve duplicates. All right. So I think I just said that. And finish up with a summary here. OK. First half, talked about view collections. Look through the collections API. There's a lot of useful stuff in there, especially with bulk operations. There is not very much material out there about this kind of stuff with collections. I think the best reference is Java Generics and Collections, a book by Naftal and Wadler. If you have follow-up questions, tweet at me on collections corner cases, and I will tweet this out as well. But here's a link to my blog where I do have the slides posted and the scripts and the source code for what I showed in JShell today. So I'm out of time. Thank you very much for your attention.